Hello everyone. Here in this session we'll discuss about three-phase system. That is the fundamental way how the soil mechanics theory gets the shape, or this is the basic way how the soil is seen in the theoretical way, and then afterwards the whole relationships ideas are developed. So we'll go into the details. So here there is a three-phase system which is shown. Means gaseous system means air, liquid system or liquid phase means water, solid phase means solid soil particles. So all the three will be there or will be present in soil. They are separated out and shown as a separate parts. Never you will see the actual soil like this, but for the development of theory purpose, we put them separately as air, water, and solid soil particles. And then using this, we define some of the terms, and there will be notations which are used for those terms, and there are interrelationships for everything. And then if you look at the final list, there are unit weights or specific weights of the soil, and here there are some new terminologies which will be coming into picture. So in the coming slides, we'll define all these terms and then we'll develop all these relationships, which will be of great help in long way in soil mechanics. So here, soil is a mixture of three phases. Three phases are the air, the water, and then soil solids. So gaseous phase is air, liquid phase is water, and solid phase is nothing but soil particles. Now if you cut a slice of soil and then try to see it microscopically, exaggerated microscopic view of cross section of soil may look something like this. All these are solid particles, and some of the space between the particles, which will be referred to as voids, is occupied by water. Some other voids are occupied by air. Both air voids and then water voids are termed as just voids, and these are particles, solid particles. Now if you put all this air together and put it on the top, that is air, and then put all this water together, put it over here, and then put all the solids and then put them at the base. Now representing the natural soil in this manner is known as three-phase representation, which will be helping us to define the new terms and develop the theory. To analyze systematically and relate weight and volume of different parts of soil, it is represented as three-phase system. What is the reason for three-phase system representation? To analyze the soil systematically and to relate the volume and weight of different parts or phases in the soil, we have to put it in a three-phase system. If all voids are filled with water, assume that all the voids are fully filled with the water, there is no air, then it becomes a particular case, an extreme case, which is a two-phase where only you have got liquid and solid state. So if all the voids are filled with water, then it leads to two-phase system, and it is also referred as fully saturated soil. On the contrary, if all the voids are fully filled up with air and no water is present, in that case, if all the voids are filled with air and no water at all, then also it is two-phase system, because you got only solid and gas, and such a soil is known as a dry soil. So where there is no water present, it is a dry soil. Where all the voids are fully filled up, it is called saturated soil. But never generally you find both the cases there will be some moisture which will be present, that is partially wet soil. Like this means some of the voids will be filled up with air, some of the voids will be filled up with water. Such soil is known as just a wet soil or a moist soil. It is not saturated, it is not fully dry, so it is in between. That's why this soil is called soil, moist soil or bulk soil or just soil mass. Okay, we'll revise some of the basics from your earlier learning. Hope all of you know specific gravity. If not, you can define it this way. It is a ratio of mass of some volume of material divided by mass of same volume of water. Look at the terms put here. Here instead of material I have put water at the bottom. Here SOME, some. Here I have made it as same, right? So if you can remember these things, that is some is there on the top and same is there in the bottom, and material on the top and then water in the, so you have defined specific gravity. And then what is the notation used for specific gravity in soil mechanics? It is capital G. Unlike the G that we till now we have referred to, which is acceleration due to gravity. So you should not confuse this G and this G. So this C is also representing gravitational constant, but here in soil mechanics it is used for representing specific gravity. Okay, there are finer things like specific gravity of soil solids and specific gravity of soil mass, but here I am defining only specific gravity. So it is a general definition for specific gravity: mass of some soil, mass of some volume of material to mass of same volume of water. Now also the specific gravity can be defined, these are all general definitions, can be defined as ratio of specific weight of a material to specific weight of water, or density of a material to density of water. Even these two definitions are very handy definitions while defining specific gravity, right? So it should be easy to remember rather than remembering this way, that is mass of something, it is easy definition is uh, specific weight of material to specific weight of water, density of material to density of water. This ratio is referred to as specific gravity. So unit weight or density of a material to the unit weight or density of water is known as specific gravity. Now what is the notation we have used for density? It is rho. Rho is known as density. Density is mass per unit volume. So rho is equal to mass divided by volume. Now we'll be using even this, these two equations, because of that it is already boxed. If you want to find out mass, we use this equation as rho into volume. If we want to find weight of a material, if we know volume, then weight will be equal to volume multiplied by gamma, the unit weight. How that expression has come? By the definition of gamma. Gamma is equal to weight divided by volume, weight per unit volume. So what is specific weight or unit weight? It is nothing but weight per unit volume, weight per unit volume. So if I want weight of a particular material, then if I know specific weight and then volume also is known, it is simply a product of volume and specific weight which will give you weight, right? Similarly, the mass. Mass is product of density and volume, right? So one should be thorough about this particular simple relations because we'll be using these relations as often as possible. So note, what is the note? Weight is measured in terms of newtons. How Newton is written with a lowercase letter n. So this has to be, weight has uh, to be written as Newton with a lowercase letter when you write it full. But if you want to denote note Newton with abbreviation, then capital N has to be used. Only smaller case letter n will not be sufficient. If you want to write it, you should write Newton this way or capital N Newton to tell the weight. And it is, that is, weight is a gravitational force. Weight is a force. Try to remember that. Weight is a force, and what is the type of force it is? It is called gravitational force because gravitational pull is putting a force on the object. That's why it is gravitational force. Weight is a gravitational force. And then when it is a force, obviously it is a vector. It has got magnitude as well as direction, right? The direction of weight is prefixed, that it is towards the center of gravity, or plumb line give the direction of force of weight. Mass is measured in grams or kilograms. It is a scalar quantity. It doesn't have any direction as such. Because of that, one value or one magnitude is sufficient to indicate the mass. So in this slide I have given you the definition of specific gravity as well as the relations of specific weight and uh, density. Okay, we'll go to the next slide. So here, weight volume relationship. What is that we are going to discuss is weight and volume relationships. Now for that, we'll be defining some of the terms here. You can just see here, number 1, 2, then there is 3, there is 4, 5, and then 6 terms we are going to define from this slide. The very important ones, very fundamental ones as far as whole of soil mechanics is concerned, and all the definitions are related to this figure, which is known as three-phase diagram. Now what is that I have indicated? If you try to understand, here air is there, water is there, soil solids are there as mentioned earlier. Volume of air is this much, volume of water is this much. All this is wide, because of that it is indicated as volume of voids. And inclusive of volume of voids and solids, totally it is known as volume of soil. So what is the term used for all the three together? It is soil. So when we say soil, you've got everything in that. Not only soil solids, but air, wet, water, everything. Okay, on the right hand side, I have indicated weight of air, weight of water, and weight of solids. Now, weight of solids, fine. Weight of water is little less. That's also fine. Compared to these two weights, weight of air is negligibly small because it is present only in the voids, and the density or specific weight of air is quite less. You never feel that there is air present unless it is packed or compressed, right? So the three-phase system of soil shows air, water, and soil solids separately as shown in figure. Now what is the first term? It is known as White's ratio. Okay, now what is the notation used? The notation used is lowercase letter e, White's ratio. What is the definition? It is the ratio of volume of voids to volume of solids. Now here we have indicated volume of voids, right? Volume of voids consists both water as well as air. Together this particular part is known as volume of voids. So that should come in the denominator divided by volume of solids. Now it is not written, but let me write. So here this is volume of solids only, that is from this to this edge. Whatever volume is there, that volume is volume of solids. Now ratio of volume of voids to volume of solids is known as voids ratio, and always it is expressed in percentage. There is one important factor or information is given. Generally, always E is greater than 0. It will not be 0 or less than 0, because when you say soil, there will be voids. Less or more voids will be there, and at times the volume of voids can be much more than the particles, the volume of particles themselves or volume of solids. In such cases, E gets more than 1. E gets more than ones. So voids ratio can be more than 1. Now, generally, volume of voids is less than volume of solids, but it is possible to have volume of voids more than volume of solids. So, E can be more than unity. Next is porosity. Now, porosity N is also a ratio. It is volume of voids once again on the top here. Here also volume of voids was there. Here also volume of voids is there. But the change is only in the denominator. In case of voids ratio, it is volume of solids, but in case of porosity, it is whole volume. Look at this figure. In this figure, it is shown that total volume is so much. Volume of voids is only this much, and volume of solids is this much. If you take the ratio of this to this, then it is voids ratio. But if you take the ratio of volume of voids to the total volume, then it is called as porosity, right? So one should be careful about this particular thing, that denominator whether it is volume of solids or it is total volume, that makes the difference of voids ratio and porosity. Now next will be volume of a degree of saturation. The term used, or the notation used for degree of saturation is SR. Sometimes it is represented just as S also, but preferably it is SR, degree of saturation. Now what is this? This is also ratio. Now ratio is volume of water. Now look here, volume of voids means it is consisting of air and water together, but only water, volume of water, that is this part, volume of water to the volume of voids, volume of water to volume of voids. Now this gives you percentage coverage of voids by the water. How much is the percentage of coverage of voids is by water? So that is nothing but degree of saturation. If all the voids are fully filled up with water, then it is SR is equal to 1 or 100%. If there is absolutely no water, then 0 divided by volume of voids will be there. Then in that case, it will be dry. So that's why in most moist soil, most of the times it is a moist soil, SR will be greater than 1, greater than 0, less than 100%. So that is degree of saturation. Again, it is expressed as percentage, expressed in percentage. Next is water content or moisture content, represented by omega or lowercase letter w. So moisture content definition or notation, first of all, omega. Definition is quite simple. It is weight of water to weight of solids. So in this case, we are taking what weight, not volume. In earlier three definitions, we have used only volumes, but when it comes to moisture content or water content denoted by W, or omega, we define it as weight of water to weight of solids expressed in percentage. So that's why in three-phase diagram we have shown weights also. So here you got a weight of water to the total weight. Total weight consists of weight of water also, weight of solids also, everything. Weight of air, which is negligible, even that if you include, then it is total weight. So here we have weight of water to weight of solids. This ratio, weight of water to weight of solids, is moisture content or water content. Then air content. AC, it is volume of air. See, water content is in terms of water, but air content is again it is a volume of air to the volume of voids. Now denominator is volume of voids. Where else denominator was same? So in degree of saturation, volume of voids is same, but there it was volume of water to volume of voids, which is known as degree of saturation. Now volume of air percent to volume of voids total is known as air content, not uh, air percentage, right? Or percentage airs, right? It is volume of air to volume of voids. Now for dry soil, AC is equal to 0. Obviously, volume of air is 100 fully. All the voids are fully filled up. Volume of voids becomes volume of voids there. So that's why in dry condition AC is 0, but in saturated condition AC is equal to 0. In dry condition AC is 100%. In saturated condition AC is 0%. In partially saturated or moist soil, this degree of saturation and AC, that is air content, have to be summed up to 1, because if you look at here, volume of water plus volume of voids, which is degree of saturation, volume of air divided by volume of voids, which is air content. If you sum up, what you get is volume of voids in the denominator and then volume of water plus volume of air in the top. So that's why SR plus AC is equal to 1 is an important equation to be remembered. Degree of saturation plus air content will make it 1. Then lastly, percentage of air voids, NA. N we have already defined, that is volume of voids to volume of total soil. So here again the denominator is kept same, volume of voids, but on the top you got volume of air, voids, and volume of air voids to the total volume is known as percentage of air voids. It's not air content. Air content is different. Air content is volume of air to volume of voids. How much is the volume occupied by air? But in last, that is percentage of air voids, it may not show something like that. Okay, thank you.